Hi everyone, and welcome to our module on basic statistics. Let's suppose we randomly selected some healthy subjects and measured their blood glucose levels. We would get a collection of readings kind of like what I've shown on the screen here. There'd be a few people with low numbers like 85, and there'd be a couple of people with higher numbers like there are some 112s in here, and then there'd be a lot of people in the middle. And if we plotted the blood glucose level on the x-axis and the number of subjects that had each level of blood glucose on the y-axis, we would get something that looks like this. There'd be some number in the middle here that was very common. A lot of people had this number in the middle. And as you went above it this way or below it that way, you would find less and less subjects had each measurement until you got down to some number that nobody had on either side. And it turns out a lot of things in nature have a distribution like this. We call this a normal or a Gaussian distribution. And it's clustered around some central number, and then it tapers out evenly as you go away from that central number, either higher or lower. And many things are like this. For example, if we looked at height of people, we could find a distribution like this. If we looked at weight, if we looked at the number of days people stay in the hospital for treatment for pneumonia, we might find a cluster around some central number of days and then tapering out as you go above or below that. So many things in nature have this distribution, and therefore we spend a lot of time talking about how to characterize it in statistics. So the first characterization of that normal distribution I want to talk about are measures of central tendency. So you notice that the curve looked something like this, and it tended to collect around a central number, and we call that a central tendency. This is the center of a normal distribution. And there are three ways to characterize that central tendency of the distribution. The first is the mean, which is the average of all the numbers. The second is the median, which is the middle number of the data set when they're all lined up in order. And the third is the mode. It's the most commonly found number. And we'll talk about all three of these now. So just to keep this simple, instead of all those blood glucose levels, let's imagine that we had 6 recordings of systolic blood pressure, and they were 90, 80, 80, 100, 110, and 120. Well, the mean would be the sum of all 6 of those numbers divided by 6. So that's very easy to get. You've probably done this many times when you average things out. And that would be 96.7 for this data set. The mode is the number that comes up most frequently. And in this data set, there are 2 examples of the number 80. So the mode would be 80. The median is the middle of the data set, and the way we determine the median is a little bit different depending on whether we have an odd number or even number of data elements. If we have an odd number of data elements, like suppose we just had 3, 80, 90, and 110, then the middle number is the median, and that would be 90. If we have an even number of data elements, let's suppose we had 80, 90, 110, and 120, then the median is going to be halfway between the middle 2 numbers, so it's going to be 100. So just remember that the median is a little bit tricky to measure. It's different from the other two, and it depends on whether there's an odd or even number of data elements. And very importantly, you have to put all the data in order to find the median. First thing you have to do is start with the lowest number and work your way up to the highest number. Once you have them laid out, you can figure out the median value. So let's get back to this chart of blood glucose levels on the x-axis and the number of subjects with each recording on the y-axis. And let's figure out where the mean, median, and mode are for this distribution. Now, I haven't given you any numbers down here on the x-axis or on the y, but we can still figure out where the mean, median, and mode are just based on the shape. So the mode is very simple. It's always the highest point. Remember, the mode is the number that occurs most commonly, and we have number of subjects over here on the y-axis. So that's the number of times that recording occurs. So whatever this blood glucose level is the most common, and that's why it's the highest point on the curve. If the data are evenly distributed, like in this example here, where there's an even number of measurements on the left side and the right side of the mode, then the mean and median are equal to the mode. So anytime you see a nice, normal, even distribution like this, the mean, median, and mode are always at the top, right in the middle. Now, data sets aren't always evenly distributed. Sometimes they are what we call skewed, and data sets can have either a positive or negative skew. And the way to keep straight what's a negative skew and what's a positive is to look for the tail. So the tail of this data set is pointing in this direction, and that's towards the negative numbers over here. So when the tail points that way, it's called negatively skewed. And the way you figure out the mode, median, and mean in a negatively skewed data set is as follows. First of all, remember that the mode is always the highest point, so that's the easiest thing to find. Next, remember that the mean is always furthest away from the mode towards the tail, and then the median occurs in the middle. And these rules will still hold up when the data are positively skewed. So here's an example of a positively skewed data set, and you can see that the tail is pointing in this direction. It's pointing away from the negative numbers over here. It's pointing towards the really highly positive numbers over here. So once again, the mode is the highest point. That's always easy to find. The mean is always the furthest away from the mode, and then the median is in the middle right here. So a couple of key points to remember on these measures of central tendency. If the distribution is equal, if it's normally distributed, then the mean, mode, and median are all equal to one another. Remember that the mode is always at the peak, and then in skewed data sets, remember that the mean is furthest away from the mode toward the tail, and the median is in the middle. And then a final point, and something that's very high yield to know for your exams, is that the mode is the least likely to be affected by outliers. When you add an outlier, it means you add one measurement that's very far away from all the others. This will have a slight effect on the mean and the median, but it's only going to affect the mode if it changes the most common number, and it's very unlikely that an outlier is going to change the most common number. That's why it's called an outlier, because it lies out and away from all the other numbers. So it's very unlikely that it's going to affect the mode. So the mode tends to stay in place when you add some unusual measurements to a data set. The mean and median are slightly affected by adding one outlier. So now I'm going to switch gears from talking about measures of central tendency and talk about measures of dispersion. Let's look at these two data sets charted on this slide. They both have a mean, median, and mode equal to 10. Their measures of central tendency are identical, but you can tell from looking at them that they're very different data sets. And what's different about these two data sets are the measures of dispersion that characterize them. So there are many different measures of dispersion that people use, but the one that you're most commonly going to see is the standard deviation. You may also see variance or standard error of the mean. Sometimes you will see z-scores, and sometimes you'll see confidence intervals. And we'll go over all 5 of these measures in the next few slides. So let's talk about standard deviation first. So standard deviation is represented by the symbol sigma right here, and this is the equation for standard deviation. Now you're very unlikely to be asked to calculate a standard deviation on step 1 of the boards, but you do need to know how to interpret standard deviations. So let me show you how you get the number, and then we'll talk about how you use it. So first let's talk about the elements of this equation right here for standard deviation. X minus X mean is the difference between each data point and the mean, and the sum of all the X minus X means is the sum of all the differences. So you're adding up how far away each data point is from the mean. Then you're going to square those differences, and then you're going to divide by the number of samples minus 1, and then you're going to take that entire thing and take the square root of it right here. So let me show you how you would do this for 2 different data sets. So we've got group 1 over here represented by these numbers right here, and the mean of all those numbers is 10. And then we've got group 2 over here represented by these numbers. So the first thing that we're going to do is determine the difference from the mean of 10 for each number. So 9, for example, is -1 from that mean, and 12, for example, is +2 away from that mean. And we're going to do the same thing over here for group 2. And so we get a collection of numbers that represent the difference of each data point from the mean. Next thing we do is square all those numbers. So this is going to eliminate all the negative numbers and give us only positive numbers, and then we add them up. So for group 1, they add up to 11 because most of the data points in group 1 are close to the mean. In group 2, they add up to 96 because the data points in group 2 are further away from the mean. And now we're going to plug it into this equation up here in the top right, and we're going to take that summed value, divide by the number of samples minus 1, which is 7 in both groups, and then take the square root of it. And what we see is that the standard deviation for group 1 is 1.24, and the standard deviation for group 2 is 3.7. This means that group 1 is much more tightly oriented around that mean compared to group 2, which is much more spread out. Even though they have the same mean, the data are more dispersed in group 2, and that's why you have a larger standard deviation in group 2. So one of the things you definitely need to know for step 1 is how much of the data set you capture if you go 1 or more standard deviations away from the mean. So let's look at this data set right here, which has a mean right at this point I'm drawing here. If we go +1 standard deviation this direction and -1 standard deviation in that direction, we will capture 68% of the data points within that range. If we go +2 standard deviations and -2 standard deviations, we will capture 95% of the data points. And finally, if we go +3 and -3, we will capture 99.7, virtually all of the data points within that range. So let's go back to those two curves I showed you before. They both have the same mean, median, and mode, but this one on the right is much more dispersed than the one on the left. Well, the rules still hold that if you go plus or minus one standard deviation on the left, you capture 68% of the data set. Same thing on the right. It's just that plus or minus one standard deviation represents more distance on the x-axis over here on the right than it does on the left. And then the same is true for the 95% intervals and the 99.7% intervals. So let me give you an example of how this kind of information might show up on an exam. Imagine that a test is administered to 200 medical students. The mean score is 80 with a standard deviation of 5. The test scores are normally distributed. How many students scored greater than 90 on the test? Well, the first thing we need to figure out is how far away from the mean 90 is. And 90 is 2 standard deviations away from the mean. The standard deviation is 5. 90 is 10 points away from that, so that's 2 standard deviations. So we know that plus or minus 2 standard deviations is 95% of the data. I've shown that down here on a picture. What you need to realize, though, is that means 5% of the data are outside this range, and that 5% is split up so that 2.5% is higher than this range and 2.5% is below this range. So this means that 2.5% of students scored above 90. That's in this top portion here, right there. And 2.5% of 200 is 5 students. And this is a type of question that often comes up on statistic exams or even in step 1. They will give you a data set and ask you to identify how many patients are in some range based on the number of standard deviations away from the mean. Most scientific literature you read will report a standard deviation, but once in a while you'll see a study that reports a variance. So remember that the standard deviation sigma is equal to the square root of all this stuff in here. Well, the variance is sigma squared, so you take away the square root, it's just the stuff under the square root sign. So sometimes this is reported instead, and it's just a different measure from standard deviation, but represents similar things. Those rules about 68% and 95% and all that don't apply to the variance. Those are only for the standard deviation. Next dispersion measure I'm going to talk about is called the standard error of the mean. And this represents how precisely we know the true population mean. In statistics, we often take a small sample and use its characteristics to estimate the characteristics of a larger population. For example, we might measure 10 systolic blood pressure readings and take the mean value and hope that that represents the mean value of a larger population of 10,000 people. The standard error of the mean gives a representation of how close we are to that true population mean. The standard error of the mean is equal to the standard deviation of our sample set divided by the square root of the number of samples. What this means is that the more samples we take, the less standard error of the mean is, the closer we are to the true mean. And this should make sense to you. If I take 10 blood pressure readings and use those to estimate the characteristics of 10,000 people, I could be way off. On the other hand, if I take 1,000 blood pressure readings and use those to estimate the characteristics of 10,000, I am probably closer to the true mean. And that's why the standard error of the mean gets lower the more samples you have. If you have a big standard deviation in your sample data set, this means you're going to have a big standard error of the mean. You're going to need a lot of samples in that case to make the standard error of the mean small. That's because the standard deviation is on top here. So if that's a big number, you have a lot of error. And the only way to cancel that out is to have lots of samples down in the denominator. A small standard deviation in your sample data set means a small standard error of the mean, and you don't need quite as many samples to still get a result with a low standard error of the mean. The next dispersion measure is the z-score, and the z-score is very simple. It's equal to the number of standard deviations you are away from the mean. So if a sample has a z-score of 0, that sample is equal to the mean. If the sample has a z-score of +1, it's 1 standard deviation above the mean, and if it has a z-score of -1, it's 1 standard deviation below the mean. So all these dotted lines here on this chart down at the bottom, which represent standard deviations away from the mean, can also be changed into z-scores by just writing -1 or +1. So just to make this very clear, in case you're ever asked to calculate it, suppose a group of students had a test grade average or mean of 79 and the standard deviation was 5. If your score on the test was 89, then your z-score would be 89 minus 79, which is 10 divided by 5 or +2. You would be 2 standard deviations away from the mean, and therefore your z-score is +2. The final measure of dispersion I want to discuss are the confidence intervals. So when you read the scientific literature, you will see most mean values reported with something called 95% confidence intervals. For example, a study of diabetic patients might report that the mean blood glucose level was 120 plus or minus 5. That plus or minus 5 is the 95% confidence intervals, and the authors are saying that this is the range in which 95% of repeated measurements would be expected to fall. The authors are saying that if you took our study of diabetic patients and repeated it, we believe that you would get a mean value of blood glucose that is similar to ours within plus or minus 5 of the mean that we got. So these confidence intervals are really for estimating population means from a sample data set. When the authors report their findings on a group of, say, 10 or 100 diabetics, they're trying to give you an estimate of what the mean would be like in the entire population of similar diabetics. So just to make this clear, suppose we take 10 samples of a population in the world that's represented by 1 million people. The mean of our 10 samples is X. How sure are we that the mean of the 1 million people is also X? The confidence intervals are what help us answer this question. So this is the equation for the 95% confidence interval down here on the bottom of the screen. It's equal to the mean value plus or minus 1.96 times the standard error of the mean. And let me show you how you would calculate that for a sample data set. So suppose we have a group of measurements and the mean value is 10, and the standard deviation is 4, and the number of measurements is 16. Well, recall from a few slides ago that the standard error of the mean is equal to the standard deviation 4 divided by the square root of the number of samples. So that would be the square root of 16. Well, the square root of 16 is 4, so this would be 4 divided by 4, and the standard error of the mean, therefore, is 1. This means our confidence interval is 10 plus or minus 1.96 times 1, and 1.96 times 1 is basically 2, so our confidence intervals are 10 plus or minus 2. So what we are saying is that we believe, based on this data set here, that 95% of repeated means would fall between 8 or 12. That's 10 plus or minus 2. And sometimes this is stated as the upper confidence limit being 12 and the lower confidence limit being 8. Now, it's very important that you don't confuse the 95% confidence interval with the standard deviation. Remember that I said that plus or minus 2 standard deviations includes 95% of a data set. That's completely different from the confidence intervals. The standard deviation is for a given group of data points. So suppose we have 10 samples. These 10 samples have a mean and a standard deviation, and 95% of these samples are going to fall between the mean plus or minus 2 standard deviations. This is purely a descriptive characteristic of the data set and all the samples. The confidence intervals, on the other hand, do not describe the sample set at all. These are an inferred value of where we think the true mean lies for a population. The confidence intervals help us tell readers of our clinical data how close we think our data set represents the population outside of our experiment. So when you see the number 95% in a question stem, don't get confused. Read the question very carefully. What are they asking for? If they say, what is the range in which 95% of the measurements in a data set fall, then they're looking for the mean plus or minus 2 standard deviations. On the other hand, if they say, what is the 95% confidence interval of the mean, then they are looking for the mean plus or minus 1.96 times the standard error of the mean. These two things are different. This is often confusing for students, and make sure you have them straight in your mind. And that concludes our module on basic statistics.